Hello scholars, welcome. Mr. Hinkle here. This lecture we're discussing foundational concepts in geologic time. It's not your time, it's not my time. It is the time of the earth, and it's a long time, vast periods of time. Since the beginning of Earth 4.6 billion years ago to today, Earth has been undergoing changes that occur on time periods longer than you and I can comprehend, and we'll look at how we got there in today's lecture, diving into foundational concepts. So, Nicholas Steno, 17th century, started to look at layers of rocks, and often for the non-geologists, this is the part of Earth that sticks out. The sedimentary layers of rock layers and beds that you see, and they look like cool rock formations. Well, they are cool rock formations, but they're also called stratigraphy, and there's specific relationships that Steno was able to identify. And he created Steno's laws of stratigraphy. So this was really huge because what Steno's laws of stratigraphy did was allow for a way to place relative ages on rocks. So his laws of stratigraphy, or I guess principles would be a more specific, accurate way of putting this. This led to the practice of relative age dating. This rock unit is older than this, and this rock unit is younger than this. And so with this knowledge, this was how the beginning of the geologic timescale was able to be created, placing different rock units in order of their relative ages. This rock unit is older than this rock unit, and this rock unit is younger than this rock unit, and we can get an idea of the relative ages in order to understand, because the geologic time scale helps us to understand significant events through Earth's history. Does not require a specific age, puts them in chronological order. Here we go, time 1, 2, 3, 4, we can see that time 1, the green layer deposits, time 2, the yellow, time 3, the red. So that means that green is older than the red, and then you have this, I guess that's purple, this is red. This red layer cuts across all of them, must be younger. So these are all examples of principles of stratigraphy. We get into that in another lecture. On the stratigraphy note, there's also William Strata Smith, who created the map that changed the world. The very first geologic map of an entire country. He dedicated his entire life to it. In fact, it's a wonderful story about, in a book titled The Map That Changed the World, about how he was able to accumulate all of the information and the skills to complete this project. And one of the biggest things that he was able to put together was that rocks with similar fossil assemblages are the same age, because in order for those rocks to have those fossils, those organisms must have been living at the same time period. So he created this principle of fossil succession, which was able to correlate rock layers across distances based on the fossils that they contained. Huge push. Now not only can you compare the relative age dates of rocks that are right next to each other, but you can compare the relative age dates of rocks that are far away from each other. So we can further enhance our understanding of a global geologic timescale. Awesome. These are both stratigraphy, these are both huge pushes in our understanding for how our Earth works and understanding our Earth through time. James Hutton, often credited with the father of as being the father of modern geology. William Smith is credited as being the father of English geology. You know, lots of fathers going on in geology, I guess. But what what James Hutton did was he developed the idea that of geologic time, really, that the Earth has been around for so long, that the Earth is very old, and in fact, whatever was happening a long time ago, the laws governing the physical processes in Earth's history must be the same governing processes that are occurring today. And he called this Uniformitarianism. It's a mouthful of syllables, but it basically means that the processes we observe today were acting in the past, so whatever's creating rocks now created rocks in the past. No vestige of a beginning, no prospect of an end. He looked and he viewed the world in terms of a very long time, in terms of geologic time. Well, he wrote a book on this, but it wasn't well received because he was very lengthy and not very direct. But Charles Lyell came in and he published a book, Principles of Geology, in 1830, right? So here we've got stratigraphy, we have geologic time, and uniformitarianism. These are going to Hutton and to Charles Lyell. So while Charles Lyell did not develop the idea of uniformitarianism, he coined the term, the present is the key to the past, and he wrote this book, Principles of Geology, that allowed the dissemination, the diffusion of this idea through the geologic community. Studying how Earth processes work today, we can also make sense of how Earth operated in the past, as well as predict the future. This is what the science of geology is predicated on. So thank you for that, Charles Lyell. Geologic time, proposed by James Hutton, but modernized by science writer enthusiast John McPhee. In 1981, he called geologic time deep time. It's a different time than you and I exist on. It is a time that changes over the last 4.6 billion years of Earth history. That's incomprehensible because you and I, we think about things in terms of minutes, hours, days, months, years, decades, and not much longer than that. Maybe centuries if we're getting into history, millennia possibly. But hundreds of millions of years, billions of years, it's hard for us to fathom. So if we put the entirety of Earth history on a 12-hour clock, this is 4.6 billion years, then we get Earth's first life somewhere around 2 a.m. We get multicellular life somewhere around 4:30 a.m. A lot is going on here. Around 10:40 p.m., now we've got fish. 11:21, now we've got the mammals and the dinosaurs. 11:37 p.m., flowering plants. And then we go to 11:59 p.m. in 59 seconds. That is going to be when humans come online. 12 hours, and we are in the last second of human history. Even this is hard for us to fathom. The whole point I'm saying is Earth has been around for so long, and humans, we've been here for just a little blink of an eye. So let's do a little thought experiment. How many zeros are on this paper? Well, each one of these boxes has 100 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 times 10 is 100. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 1, 2, 3, 4, 5. So if we do some math here, we could say 5 times 10 times 100. It's going to be a 5 with 1, 2, 3 zeros. 5,000. There's 5,000 zeros on this page. So let's take one piece of paper and say that this piece of paper represents 5,000 years of Earth history. So, okay. How many sheets of paper would I need for 1,000,000 years? Well, that would be 200 sheets of paper. How many sheets of paper would I need for 1,000,000,000 years? That would be 200,000 sheets of paper. Let's keep going. The Earth is 4.566 according to this one. It varies based on your sources, roughly 4.6, divided by 5,000, which is one sheet of paper, 5,000 years old, means we would need 913,200 sheets of paper. 913,000. I still don't know how many that is. So we can say copy paper comes in bundles that have 500 sheets of paper. So, okay, each one of these 500 sheets of paper with 5,000 zeros on it, that's 25,000 years being represented here. If we divide that 500 sheets into how many pieces of paper we would need, we get 1,826. So stack 1,826 of these high, each with 5,000 zeros. And now we get the age of the Earth, 4.6 billion years old. And this whole experiment is for us to go, whoa, the Earth is really old. In fact, you'd have to stack almost 2,000 reams of paper, each piece of paper representing 5,000 years just to represent it. That is a very long time. So we have these ideas in geology that have really helped shape the modern science. Stratigraphy is a big one. Uniformitarianism, which I didn't write, but we can put it here. Uniformitarianism. How many syllables is that? A lot. And deep time, or geologic time. Thank you so much. I'll see you again.